phone as a mic temporarily until we fix on the stream?
Yeah, sure.
And this was supposed to be animated, but it's not, but that's okay. So first of all, I want to talk about credible mechanisms. This was an idea that was introduced by Lee and Akbapur 2020. They wanted to ask at a high level, what happens if the entity that is operationalizing a mechanism is able to deviate from the intended rules of the mechanism? So maybe a canonical example to have in mind, which you're all familiar with in this audience, I think, is a second price auction would not be credible because there are deviations available that are not visible to the participants. And they formalized this. So I want to spend a minute on this. So they said that a rule describes an intended behavior. For example, the intended behavior might be take all bids and run a first price auction. They describe the concept of a safe deviation. This is a deviation from the rule that generates an output for which there exists an input consistent with the rule, given each participant's knowledge of the input. So, you may know your bid, you may not know the other bids, and then you observe the outcome. Is the outcome consistent with some possible completion of the input? If it is, then this is a safe deviation. The entity operationalizing the mechanism may have deviated from the intended behavior, but in a way that is not observable to any party based on what they know. And then they say that a rule is credible if there is no profitable safe deviation. So they don't require there to be no safe deviations, but they require there to be no useful safe deviations. So I think it's useful to imagine that deviations that are not safe are sanctioned in some way. You're staking your reputation as a mechanism entity on following the rule, at least up until the point where your deviations can be caught. There are other things you can do that nobody will know about. You're not making any guarantees in that regard. And we still want to be able to say useful things about the mechanism. And what they proved in this paper, they proved a trilemma, which I'm not going to step through in detail, but they proved, for example, that revenue optimal first price auctions are credible, but second price auctions are not credible. And I think when we think about commitment, then I'm going to try to tie things into commitment. I think we could say that credibility gives a self-interested mechanism commitment power. If my mechanism rules are credible, then I can commit in a credible way to follow those rules. It is incentive compatible for me to follow them and not to use a safe deviation. Okay, so this notion of credibility, which now you can kind of situate this in the DeFi space. So in the DeFi space, and let's think about transaction ordering into an AMM. In the DeFi space, a rule is an intended behavior. It might be take all transactions that you have seen and follow a particular sequencing methods to order those transactions onto an AMM. That might be the intended behavior. And then a safe deviation is one that, again, generates an output for which there is an input that is consistent with the rule, given knowledge of the input. I think oftentimes when we think about blockchain, we will think about the input as being observable. That is the input that is used as being observable. So when I think about DeFi, for example, concretely, we can all observe the transactions that were pushed through Uniswap in that block. So in that sense, we all have information about the input. And what does it mean to be credible? It means that and so a safe deviation is any deviation where if there's some space, either if there's some space in the rules, you still are following the requirements of the rule, or a deviation where you perturb the input in some way. Right? You're allowed to perturb the input. It's just that you have to follow the rule given what people see about the input. And here the input is all of the transactions that are written into the block. I'm going to mention in a second a result we have, and it's just a slight tweak on the credibility definition. So the definition I gave you earlier is there is no profitable safe deviation. The definition I'm now going to use is that any profitable safe deviation from the rule still achieves design goals that we care about. So there may be deviations, and I'm okay with that as long as any deviations that the mechanism chooses to follow still lead to properties that are good for me. For example, a property I might care about in the DeFi context is I'm okay with MEV, but only if the execution price on the transaction that is MEV'd is good in a way that we could formalize. And again, think about other deviations being sanctioned. So this is credibility where I say, I'm going to follow this particular sequencing rule. If you ever see, based on what you see about the input that I'm using, that I didn't follow the rule, you can sanction me. Everybody will know that I deviated. And now going forward, people will choose not to submit transactions to my mechanism. So here, credibility gives a self-interested party commitment power to achieve desiderata, where again, desiderata might be what we could think about informally as tolerable MEV. It is incentive compatible for me to achieve these desiderata, even if I might choose to use some safe deviations. So we have a forthcoming paper that I'm not going to get into in any detail other than to advertise it here. You can ask me about it later if we want to go there, which is coming up in stock, where we give a verifiable sequencing rule that ensures this kind of tolerable MEV property. So it ensures that for any executed transaction A, either the price of A is as good as if A was the only order to execute, or no MEV is gained by executing A. And you could think about, for example, builders and relays choosing to adopt that rule. And then now they are committing to be observed and have staked their reputation on not deviating. So they're committing, and the question is whether those rules have nice properties. That's the first thing that I wanted to talk about, is the role of credibility. Second thing, I want to now jump back in time and talk about this idea of faithful implementations. The backdrop to this was that algorithmic mechanism design started in around 1999, 2000s. There was a flurry of activity around polynomial time mechanisms. And then some people, in particular Joan Feigenbaum and Scott Schenker, started thinking about what would happen if we had distributed algorithms that were implementing the mechanisms. And so now the question wasn't so much, is there a polynomial time centralized algorithm that can operationalize the rules of a mechanism, but is there a decentralized algorithm with nice communication complexity and computational complexity that can run the algorithm? And they wrote some very nice papers. I would encourage you to read them. The question they didn't ask is they didn't ask whether it was incentive aligned to follow the distributed algorithm. So they said, here's a distributed algorithm where if it is run, it will effectively compute the output of the mechanism. And they wanted mechanisms because mechanisms were providing incentive alignment around inputs, but they were not insisting that parties wouldn't want to deviate from the algorithm itself. And yet at the same time, their motivating story were often things like BGP, Border Gateway Protocol for autonomous systems on the internet, which are self-interested parties executing decentralized algorithms. You know, there's no reason to really think they would choose to follow the algorithm if they could benefit by deviating from it. And so what we did in this work was we wanted to add this additional criterion of incentive alignment with choosing to follow the algorithm. And that's what I mean by a faithful implementation. So there was a PODC paper, there were 2 RMAS papers, so it's nice that we're adjacent to RMAS today. I called this specification faithfulness. So it's work with Jeff Schneidman, and I want to contrast it to credibility. So in credibility, there is a privileged party, say a mechanism, that receives inputs, can tamper with them in various ways, and then selects an output. When we were thinking about faithfulness, we didn't have any kind of center, any privileged party. We wanted a fully distributed system. So I would often draw these types of pictures. Here's a center. And here it's like, no, you take the rules of the mechanism and you give them to all of the participants in the system, and they're all doing some part of the distributed computation. And we wanted all of that communication and computation to be in equilibrium. So it's a weaker form of commitment reflecting that multi-party aspect. It says it's incentive aligned for me to follow my part of the mechanism rules, given that others do the same. There's an equilibrium notion. All right, and what we did is we asked the question, can following a protocol be made in ex post Nash equilibrium? Roughly, this says, as long as others follow the protocol, then whatever the inputs, you also want to follow the protocol, whatever the private inputs. That's the ex post aspect of it. And if it's true, then we say that the specification is faithful. We formalized it by breaking up the strategy now of a agent represents the computation that they're doing, and we thought about that in terms of a revelation component, a computation component, and a message passing component. So revelation is computation you're doing that is touching your private input. Computation is work you're doing that is depending on inputs that you've received, and message passing is you sending messages to others. And we developed a proof recipe that I will flash and not spend a lot of time on, where we first of all defines this notion of algorithm compatible, which says that an agent will choose to follow the suggested computation in equilibrium. Communication compatible, an agent will choose to follow the suggested message passing in equilibrium. And then we strengthened AC, and we said, well, strong AC is that you will choose to follow your suggested computation, whatever you do in regard to your revelation action and your communication action. So assuming others do what they're supposed to be doing, but even if you were to deviate in arbitrary ways for revelation and message passing, it's still incentive aligned for you to do the computation correctly. And you can similarly strengthen communication compatibility. And then we can prove, it's quite easy to then prove that if a mechanism is strategy proof and you have a correct distributed specification that is strong AC and strong CC, then the specification will be faithful. So then the game is all about how to establish these properties. And we provided techniques for that in these papers. RMS 04, almost 20 years ago, it's hard to believe. Distributed VCG methods. We had our BGP protocol, which was in PODC, and then a more general distributed optimization algorithm in RMS 06. So that's about faithfulness. Go back 1 year now, strategy-proof computing. This is something I was playing around with pretty early as a professor at Harvard, and I remember giving this talk, actually. It was in a little room in Acapulco at IJCAI in 2003. And I don't think I've talked about it since. So thank you for giving me the chance. I think this paper has 10 citations. So I was developing this notion of what it would mean to have something called strategy-proof computing. And I'd been motivated by what's known as the end-to-end principle in network systems, where somehow you You don't try to do too much in the network. You facilitate innovation on the edges. And I wanted to kind of think through what would that mean for mechanism design. And my main idea was, well, you don't want there to be one designer. You want there to be innovation amongst mechanism designers. You want anybody to be able to deploy a mechanism and have kind of a competitive landscape for which mechanisms get used. And then I was thinking through, okay, what would that mean? How might that work? Is there an AI agenda here? One thing I decided was that I wanted each mechanism to be strategy proof, at least kind of locally for the things that it's doing. And so what I mean by that is that strategy proofness doesn't compose very well. If you're trying to buy a bundle of stuff and I give you a strategy proof mechanism for one part of the stuff you want to buy and a strategy proof mechanism for the second part, it doesn't mean that your dominant strategy is to bid truthfully for this part and bid truthfully for this part, because you might not put everything together correctly. So there's this composability problem, which I raised in the paper. But what I did want to insist is that if somebody deploys a mechanism to allocate this particular bundle of resources, that mechanism should be strategy proof in a particular way and should be certified as such. So this is the abstract of the paper. Wanted to support continued innovation and competition, focusing on resource allocation, arbitration of resources. And by individual users can treat other resources as their own. This is the notion of simplicity that comes from strategy proofness, that you shouldn't have to game in the requests that you're making for resources. You should just be able to describe what you're interested in, just as you would if you weren't competing with others for those resources. And I laid out some challenges. I'm just going to tell you what they were. And then I will point you to the paper, which I think we've posted on the webpage. So I laid out 5 guiding principles, and then I laid out 5 AI challenges. Principles were we should care about incentives. We should be focused on utility, not utilization. We want incentive compatibility. We want openness, and we want things to be decentralized. And then the challenges were design, were how to describe what it is your mechanism does and who it is designed for and what properties does it have. How we can verify in a data-driven way the incentive properties of the mechanism. Because I had in mind that the infrastructure, which was vaguely discussed in the paper, is monitoring inputs and outputs to these mechanisms and is able to, by looking at the trace of inputs and outputs, notice violations in strategy proofness. I say, I sanction you. You are not strategy proof. I have proof. By looking at the things you've been doing over time, I can see you're not strategy proof. That's the way I was thinking about this. And we did later work on that. I have a paper on that verification step. Competitionality, and I'd forgotten about this until I looked at the paper yesterday. I talked about the idea of learning, using machine learning to try to design mechanisms as well in that paper. So then fast forward to this year, where we are using machine learning to design mechanisms. And I've been kind of working on this idea of differentiable economics now for a few years with a number of collaborators. And the particular project that I wanted to briefly mention is about contract design. So it fits with commitment devices. So, and I didn't mention commitments here, but what I wanted to say is that assume the ability to commit to the rules of a mechanism, that you are not going to change the rules of the mechanism. This was an implicit assumption in my paper, that you can deploy something and you will not change it, which today I think we can roughly do that. So that's good. Differential economics. This was something we started in 2017. Whole bunch of co-authors, including Zhefeng and Sai Ravindranath. More recently, Jeff Zhang and Tonghan Wang in my research group. Simple idea. It says, okay, let's represent the rules of a mechanism via a differentiable function, neural network. And let's use differentiable techniques to try to optimize the rules of the mechanism. The technical challenge is, I mean, there are a few, but one technical challenge is that you need incentive compatibility. So if I gave the network the objective of minimizing negated revenue or maximizing expected revenue, so if we say your loss function is negated revenue, well, it's going to do that in a non-incentive compatible way. It's going to kind of charge you your bid, which of course is not sensible economically. So we have to have a way to regularize, penalize in some way the mechanisms that are learned, which we do in this research in various ways. Just as a quick example, before I talk about contracts, in the first work, we talked about optimal auction design. Very simple example, just with one bidder, just to illustrate what happens. And you can have auctions for single bidders. I know it sounds a little silly, but actually digital goods do tend to decompose across bidders because they're what's called a non-rival good. So suppose we had a single bidder with an additive valuation function, uniform 0-1 for item 1, uniform 0-1 for item 2. The theoretical economics literature tells us what the optimal design of an auction is. This is what it is. It says that if the value is in this space, less than this number for item 1, less than this for item 2, then don't allocate. If your value is high for both, allocate. If it's high for 1 but not 2, allocate item 1. High for 2 but not 1, allocate item 2. And then the payments follow from typical auction theory. So if you just want to decompose it down, this is the allocation rule from theory for item 1, and this is the allocation rule from theory for item 2. So it has this threshold kind of structure to it. And when you train the network, you learn things that look like this. So this is the density plot of a tanh-based neural network. So you can see it kind of smooths out the boundaries, but it's approximately doing what it should do. Okay, so just, I think it's basically my last slide. So hopefully we will have enough time for discussion. Working paper led by Tonghan Wang in my research group on using this technique for optimal contracts design. Let me tell you what I mean by a contract here, and I mean it in the very classical sense from economics. So we think here about there being an agent with unobservable, costly actions, each action causing a distribution on observable outcomes, and there being a principal, another actor in the system, with value for the outcomes. So think about the agent as your contractor. If you're improving your house, you don't watch what the contractor does all the time, but based on the behavior of the contractor, your house is high quality or not, is on time or late, and you can contract on payments with the, you can offer your contractor payments that are conditioned on whether or not the outcome is high quality or low quality, on time or late. And the goal is in our work, is to learn a contract. What is a contract? It's these outcome contingent payments to maximize the expected utility of the principal, which is so think about for a given contract, this induces a distribution over outcomes. You have an expected value for that. You have an expected cost because you're paying, and you want to find out of all possible contracts, the one that is best. So what we do here is we recognize that if you think about the design space, this is a bit washed out, but this is a two-dimensional contract space showing the utility function of the principal. The utility function of the principal as you move in contract space is discontinuous, because as you move from one contract to another, the principal's best response, the agent's best response action can change. And that can lead to a discontinuity in the utility to the principal. And so we noticed that, for example, RailU networks are piecewise continuous approximations. So we introduced a new network architecture which gives a discontinuity, which is appropriate to modeling this problem. So we learn the utility function to the principal, and then we do inference on that space to find the optimal contract. Going back to commitment here, this is assuming in the background the ability to commit to a contract. If you can commit to a contract, which are these outcome contingent payments, then there's a contract design problem that can be solved using machine learning. So just to wrap up, I wanted to give you these 4 illustrations on alignment and commitments. Emphasize that each of them has a different notion of commitments. In credible mechanisms, your commitment power comes from it being in your own self-interest, not to use a safe deviation, or in your own interest to only use deviations that are tolerable. In the faithful implementation space, your commitment power comes from it being in your self-interest to follow the rules of the protocol as long as others are doing the same. In strategy-proof computing, we assumed in that work that different parties are able to commit to the rules of mechanisms. And then we argued that it would be in the self-interest of a party to publish a strategy-proof mechanism because the infrastructure is going to run a reputation system to catch a deviation. And then in this optimal contract design work, we're assuming the ability to commit to a contract, which is an outcome contingent payment rule, and using machine learning to design that commitment device. That's all I had. I wanted to kind of share this with you because I think these are all examples where I hope that ideas from distributed AI, multi-agent systems research, econ CS research can continue to get picked up in the crypto space. And I'm guessing that a bunch of you are building out and designing things in that space. Thanks.
I'm curious if the kind of the 5 challenges that you mentioned in the data do you think any of them have been kind of, I'm sorry, exactly what they all want now, but yeah, which ones do you kind of currently see as the kind of biggest outstanding ones that are still here? Which ones do you think we've actually made a bit of progress on? The sources of systems, yeah, what does that stand in place of behavior writing?
Yeah, great. I would say good progress on mechanism design, good progress on the automation of mechanism design. People haven't really worried so much about developing languages to describe the properties of mechanisms. A lot of work on languages to describe inputs to mechanisms, but not that whole massive question of how you describe the mechanism itself. And I don't think there's been a lot of work on this idea that I'm describing in that paper of looking at traces of input-output decisions from mechanisms and developing algorithms that can give with high probability guarantees that in fact the mechanism is strategy proof. We did some work on this, like the space for more work. And maybe there's a whole different approach to this, which is more based on modern cryptographic techniques, which we weren't thinking about here. Maybe we can chat a little bit about that. Competitionality is something that people are very aware of. There was some work on this after I wrote this paper. There was a paper by Moalan and Misan that gave one way in which you can compose factors together. We also did some work where we talked about mechanisms for options. So you don't buy the resource, you buy an option to use the resource, which gives you better compositionality because you're not exposed to having to buy the resource. We did some work on that, but I think it was Mike Wallman that once said to me, he said, you're never going to have a combinatorial auction for all of the resources in the world. And so there are always going to be boundaries between mechanisms. And I think there still haven't been very much work on kind of understanding that space. I suppose the price of anarchy work in the theoretical computer science community has proved some things about what happens if you use very simple decoupled auctions that I suppose you could think about as a competitionality argument.
Yeah, building off the description point, I'm curious about sort of the notion of credibility and faithfulness, and thinking about how like other economic security models, in like the blockchain space have played out. And I know if I understood correctly, in the notion of faithfulness comes from like a notion of equilibrium where you consider only deviation of individual agents. But another concept people look at often is like collusion thresholds. And then another sort of like angle as well is looking at sort of the economic security budget, in that if there's some unbounded activity from users like the blockchain, you never know the volumes of money moving around. There might be some like upper bound at which point like the mechanism just uses its faithfulness or credibility or whatever. So I'm curious if you've thought of other or extensions to the notions of faithfulness and credibility that cover these kind of security concepts.
Yeah, great question. I mean, few things to say. First of all, I think that coalitional refinements that what X talks about can certainly be defined. We don't know that people have really taken either credibility or faithfulness though yet and done that. The most constructive, positive thinking I've done about coalitional phase is that could we handle coalitional deviations within the automated mechanism design framework when we learn mechanisms? Because what we do in that framework is we penalize unilateral deviations with a loss function. I didn't talk about it, but that's roughly what we did. So you could penalize coalitional deviations, and I think you could use that framing to be able to build mechanisms that are more robust. I'm generally pretty bullish about using machine learning techniques to automate that incentive design loop, and I think it's quite flexible. So I think if there are coalitional things you care about or other things, it would be interesting to study it in that framing. The other thing I would say is there was some nice work early on by people like Vanessa Teague and Jim Halpern on rational secret sharing models. There's a secret sharing multi-party computation literature that takes the classical crypto assumptions adversaries that can behave in arbitrary ways. And talks about robustness against some fraction of the participants deviating. There would work again in the mid-2000s. You can say, okay, what if the participants are not Byzantine in that way, but are rational actors in some ways these times? And that gave some kind of coalitional robustness properties there. Did that cover your questions? You might have another set of questions, I think.
Yeah, a lot of questions. Was that, you say Joe Halpern?
Yeah, Joe Halpern and Vanessa Teague, and then we had follow-up week. Leo Vidanen and myself had a follow-up paper on that as well. Yeah. Thanks.
Okay, when you what's in that compositionality? Yes, so like and beyond commitments, what kind of techniques can we use to achieve these?
Yeah. Yeah, I'm still not sure I have anything particularly excited to say in particular about commitment with compositionality and the way those two come together. But hopefully we can get there during the conversation we have today. I think the best thing I can say in regards to compositionality is, first of all, just contrast it and differentiate privacy. You know, one of the things people love about differential privacy is it's composable. And so it's always been incredibly frustrating to me that these mechanism design settings seem to not be able to achieve the same properties, which is why we did think about it through options a little bit. But I think the best thing to say is, and actually that was part of my motivation for strategy-proof computing. Part of my strategy-proof computing notion was to let there be innovation where mechanism designers could kind of draw the boundaries in an appropriate way in the resource space. Yeah, resource space could be, could literally be spatial, could be temporal, could be other things, but try to draw boundaries in ways where you draw the boundaries that match the separability of utility functions for, say, the majority of participants in the system, so that their problems will broadly break along, this way and this way, and they can independently make decisions here and then make decisions here. As I talk to you, I wouldn't be surprised if there are things we can do by thinking about some of the graphical modeling techniques that people use for probabilistic models, where these conditional independencies and DAG structures, where you're willing to make assumptions about the lack of dependencies between random variables in the world. There may be things like that we can also leverage, or kind of ideas like that. All the graphical representations we can write down that capture the types of conditional independencies, where if I give you this resource, then now your value for these resources are decoupled. Yeah, you got to independently decide over here, and then independently decide over here. This is the type of way that we should be thinking if we want to think about how to break apart problems. But maybe we shouldn't be that naive, and maybe we should just be thinking about how to build infrastructure so that other people can kind of move their mechanism domains around and try to be smart in a way that helps users.
Kind of a follow-up question to elaborate on that somewhere. And something from your other paper on strategy-proof computing was that it would be the market itself that would find those regions. And now you're talking more of a top-down kind of thing with the probability. So, what do you think it's more promising there for the meta problem of not designing the mechanism in but partition?
Yeah, I mean, I would say definitely bottom up. But still, those participants will still need the right heuristics to know how to carve out the resource space. By the way, I did do a lot of work on common auctions, so that's something that I've thought a lot about. And there are various preference representations in that literature that capture these types of independencies or couplings. So I think there are things we can borrow, but yeah, I would say try to build infrastructures that allow for innovations over time. Probably not very controversial in some sense.
So you mentioned a couple of times credibility and mechanisms, especially in the first paper. And I was wondering what your thoughts have been over the years, starting with now, about how to enforce those. We've talked about reputation at one point, but how has this been part of the research? Because at some point, let's say you can verify a sequence of transactions as not being restricted, or there was a deviation from what you were expected to do. I was just wondering how you thought, what your thoughts are on enforcement.
Yeah, thanks. I did initially think about that as more of a kind of an incentive ecosystem, like a reputation system where there are checkers that are motivated to find problems and call out the problems. But there was a period of time when I did work on using homomorphic encryption type ideas. We were using a pretty lightweight form of that, where the way we were modeling it was we didn't want to prevent the mechanism getting knowledge of the inputs, but we did want the mechanism to have to prove to anybody that the computation was done correctly. And yeah, we were using various, we're calling random log techniques with straight line computation. I can talk to you about it more offline, but there's techniques as a work with Michael Rabin, he was not retired, and Christopher at Harvard. And there it was this prove verify model where you run the mechanism and then you could deviate, but if you deviated, you wouldn't be able to prove that you've done the right thing. Right? So thinking about that, but things like normal non-decentralized exchanges, but there are all these probably dark holes in finance where it became apparent over the years that banks were not able to credibly commit, not to use information they weren't supposed to use. And so I wanted to know whether we could use crypto techniques to have them commit to a rule and then not be able to prove that they haven't deviated. So I suppose all I'm trying to say is that over time, and then, in today's world with smart contracts and other technologies, I think we have much more ability to commit to rules. There is always still the question about what happens if you, okay, I mean, there are various flavors of that, of course. It could be literally the, I have no available deviations, but I think typically in the crypto space, I can commit to the rule, but I cannot get the inputs there necessarily, right? So the malfeasance is then playing with the inputs that hit that function. And that's why I think that combining that ability to commit to a function that acts on whatever inputs it does get with credibility, which is bringing incentives to the table to complement that, I think that works really nicely together. Because then you've got the incentive alignments around the inputs being correct or not modified in a bad way, with the crypto providing protection against the input output will not be good. Yeah.
I wanted to expand on this a bit, and I wanted to see if you have any intuitions on how can we prove faithfulness of a optimal smart contract that's based on a machine learning model. Like, would we want to prove the learning? Do we want to prove that to us talks using correct data, or like,
what would it even mean for a smart contract not to be faithful? I suppose is where my mind is going. Again, it's about inputs, right? So, is it a smart contract a lot closer to what I framed as being something more where credibility would be?
absolutely, but if the contract itself is created by an engine, it's like a machine learning model, something like that, then wouldn't you want to prove data to the issue?
Yeah, maybe I could take your question this way, but feel free to push back on. This is actually really interesting, I think. Could we use differentiable economics to learn credible mechanisms? I think that's where my mind went when you said that. But here's where I in my group, we should mention that on the verifiable sequencing rules work for NEB. I've been thinking a lot about credibility in the blockchain space, and can also continue that conversation. But I think credibility is very nicely suited to blockchain. And I think that would be super interesting. I never thought about using differential econ for credibility as a constraint.
Do you have any intuitions of the shape of that, right? It's terminal to the same treatment as sender compatibility constraint.
Yeah. So I think so. I think that would be where I would start. I would code up the types of deviations that are represented through the credibility concept, and I would want to penalize them when they go against the desiderata.
I originally tried to do in the context of you think about that, but it wasn't because some of his work is about iterative, but mostly so like the odds.
Echoism. But there are other limitations, and like some of them it's almost fundamental.
Right. So adoption is definitely a challenge. What I'm thinking about in response to your question is that you don't want to leave everything to a reputation mechanism. Reputation mechanisms may not bootstrap. I mean, right? Nobody starts using my mechanism, then how can it build a reputation? By the way, there's an interesting story about the launch of eBay in that regard. eBay launched in 1995, and as of 1996, had a reputation system. And as far as I know, the internet's first ever reputation system. And they designed a two-sided reputation mechanism where buyers could leave feedback on sellers and sellers on buyers. And people always ask, why would they have sellers provide reputation feedback on buyers? One reason that's given is the buyers can build a reputation as a buyer and then use that reputation as a seller. So there's this idea of letting reputation be portable from kind of one way you're acting into another way you're acting. So maybe one way to think about bootstrapping reputation and getting better efficiency that is to think about whether or not you can contribute your reputation to others, a little bit like the way we think about things like page rank type mechanisms. But I think our crypto ecosystem is not that yet. Also there. And I'm also thinking that it shouldn't just be about reputation and collecting data. It should be about proving things as well. We don't want all of it to be about having to wait and see what happens. We want as much of it as we can be about provable properties that anybody can check.
On the reputation side of things, there's also this question then of our, I don't know what the correct property is, but how like game the reputation system is.
Yeah. And it's actually you get all of the same problems at the meta level. Yeah. And there's lots of interesting work on attacks on reputations. Page rank is famously not robust to simple attacks. You get a loose of people punting each other. The pump feedback score around so that the random walk will sit this verdict behind holding it there. And so John Cockcroft wrote a paper in 2008 where we used hitting time, which is another stochastic process, and proved that that was simple. It was being worked there as well. I mean, any questions you guys ask me, I can probably point to somebody in the past 20 years, but exactly like what is the right thing for the problem you're grappling with, I'm not sure.
Yeah, the references are appreciated.
Yeah,
sure. Once I will finish my text, but can you pull the reference again?
I have a question. I want to kind of go back to the one sec. The kind people make a commitment to attack your deploy commitments. So you were mentioning like, well, what are some productive ways to think about coalitional mechanisms, and we also making the the blockchain it is easy to credibly need to a set of rules, but the instance the rules can be manipulated, as in the case, say, censorship or whatever. And over there, the way people usually solve these problems is to delegate the job, actually processing the input, providing the input to one person.
to a trusted person.
Yeah, or like you somehow encourage those two parties, one party to hold the data availability, the other party to hold the actual execution mechanism, encourage competition between them as much as possible. However, blockchains also, make mechanism design deployment too easy in the sense that it is super easy for someone to deploy another credit mechanism for those two parties to use. And then it just, kind of never ends up being the incentive can't be engineered right. It's like what I think I guess what are some constructive ways to think about traditional
So let's be precise as well. Coalitional, and really referring to coalitions of participants in the mechanism, whereas now I think you're thinking about coalitions of mechanisms. Am I right?
Yes.
Yeah. Coalitions of mechanisms that are somehow setting themselves up to be able to work together to defeat the divine intent, some separation of concerns, let's say. I don't think I've thought about this. You may have defeated me in relation to the mechanisms. I mean, most mechanism design that you just take the stance of a single mechanism design. So even the notion of the being mechanism design in the context of multiple mechanisms is relatively understudied. And then the notion, I'm making excuses, but now the notion of like coalitions of mechanisms, I think is even less another study. But let's see, do I have anything to say?
Yeah, I mean, like it's, we kind of see that because very often, and people, many people want to deploy such things. For example, somebody builds an Oracle service, and people want to deploy some additional mechanisms to allow the Oracle service sound like anything else, something like that.
Yeah, I see. I've often, so sometimes I've adopted a notion of that the existence of the mechanism shouldn't create new incentive concerns. Somehow, one thing that came to mind when you said that is work on information elicitation. But that work typically assumes that the only thing you're trying to do with the participants is to get the information you're sharing. You don't have any outside, so it doesn't work to the Oracle. But what you do want in that case is that if you deploy an information elicitation mechanism, you don't want it to introduce new incentives to be acting in some different way in the world to change the events that then being other useful where the impression inspection. So you can try to formalize the types of interactions that you don't want, and then try to prove that the mechanism is robust against them. Yeah, that wasn't very clear. We'd be thinking a little bit about that in the incubation space. Yeah.
Sounds like a job for AI.
There we go. And where I get stuck, I wait in your guess, or we think about AI.
Oh yeah. So anybody has any last questions? That was
Contrary problems. What can you solve with this different methods?
The differential economic thing. Contracting. So you're correct. The answer at the moment is which is not very satisfying because I'm still working. Okay, so the computational technique for contract design that most people would use for problems like what I described would be using linear programming, where you solve you solve a separate linear program for every action. And so that if you have a very large number of actions, you have a very large amount of computation to be able to solve the contract design. We avoid that here. In fact, here the actions never commence the representation. The data that we see is contract design, and then the utility to the so it's scale, but I don't think I yet have a satisfying answer for the requirements because interesting actually that the as far as I know the kind of applied contract design literature is a little bit less developed than the applied ocean design literature. And so I haven't yet found kind of the right initial problem for this economics literature to take this down.
We usually sort of multi-dimensional.
Yeah, so multi-dimensional. Yeah, so multi-dimensional. Here do you mean multi-dimensional? Yeah. We've been thinking about a related problem for data market design, which sounds a bit like contract. Yeah. So if you have anything in mind, we could try to take it. This is very new, so we haven't tried to apply it to anything really serious yet. Yeah.
So one of the soft challenges was like about auditing. I forgot what the name.
Basic verification.
Yeah, though we after this question, we're gonna probably start this.
Okay.
Yeah, and you mentioned like that you weren't thinking about modern.
At the time,
We're trying to like zero knowledge mechanism.
Yeah.
Do you think that kind of solves one of that?
Not obviously. And I think even just smart contracts where anybody can look at the description of the contracts, not obviously, because the property I'm interested in proving something about is strategy proofness, which is a kind of a derived property of the function. And so even if I describe the function to you, it may not be, I don't think we know very much about how tractable it is. There's a little bit of very recent work, but I don't remember the authors. But I think we don't really understand how tractable it is to somehow query that function and decide whether it is strategy proof or not. So, zero knowledge techniques. Actually, I think Yannick and Tressi work on the zero knowledge for incentive or economic properties. So maybe that's where
it's also a key example of which is developing the language.
Right.
Right.
So it's the idea just that like you need a mathematical proof to complete the journal, but you want to do it first when you don't have mathematical proof, but you do have in practice how the data that we have.
Somehow zero knowledge in the null sense would just prove that you correctly function. Really, with the correct syntax. It wouldn't prove the property of the function.
Right. Yeah, and I think that's the zero knowledge thing, right? Is to commit to a mechanism.
I guess what you could prove, it's not really satisfactory, but you could prove easily that there's no useful unilateral deviation in a sort of it. So that's something to prove. That's well defined. That's not bad. All right, thank you.